Good morning, everyone. Give me 1 second, connect this. Can someone confirm me if you can hear me? Hello? Good. Give me 1 minute to connect this device. One second. Okay, so what I'm going to do today, I did not actually record these 2 last lectures. So what I'm going to do, I'm going to spend some time to deliver them so that the recording will be there for other students, and then I will do use the remaining time to start doing the homework. So the plan is to do all the homeworks in class from homework 1 to 11. Okay, the good thing about this lecture is this lecture is very familiar, should be very familiar to lecture 1, so which we will review today. So then you can see the connection. All this time, some simple concept I introduced in lecture 1, like the velocity of the falling object. Then we used a numerical method to solve that problem, how to compute the velocity of a falling object. Now, we learned a lot of numerical concept over this time, and then we know a lot of theory. And when we go back, and I'm sure you will have a different meaning when you review that. So having said that, let me introduce this today's lecture, which is ordinary differential equation. So what is ordinary differential equation, and what we are trying to do here? We are trying to solve an ordinary differential equation using numerical method. So for example, equation 1 here and equation 2 here are an example of differential equation. Usually we have a function fx is some ax squared plus bx plus c. That's a regular function. But if you have if you have a function like this, f prime x is ax plus b, then that's a differential equation. That's the dfx by dx is ax plus b. So this is called a differential equation. Particularly the one I wrote there, that is called an ordinary differential equation. So what is the difference between an ordinary differential equation and partial differential equation? Partial differential equation is the next lecture. Ordinary differential equation will only have one variable. This is an example of ordinary equation. 3 is an example of ordinary differential equation. Why? There's only y, the one is being the the derivative is with respect to only one variable. Always, if you look at this, the derivative is always with respect to, there are many orders, first order, second order, third order, like that. But the derivative is always with respect to one variable. Even if the function can be of many variables, but other variables should be known. But if you look at equation 2, the derivative with respect to two variables, dx and then dy is set. So that's not an ordinary differential equation. That is a partial differential equation. Partial differential equation. Why? The derivative is 2. You can have n different variables all fall under the category of partial differential equation. So one variable, multivariable. So we can do one variable in this. Well, I am showing full screen. So my whole thing, I mean, you want me to zoom like this? Is that what you mean? Yeah, I can zoom like that, but yeah, what you can do is, you can make the window a little bit bigger and so on. But yeah, when I go closer to the equation, I will zoom like that. So how we solve this partial ordinary differential equation using numerical method. That's the focus of this lecture, and you might remember this name, Euler's method, which we introduced in lecture 1. So yi plus 1 is yi plus h time f xi yi time plus error or odd error. In lecture 1, we did not talk about error, order of h squared and whatnot, but now we know what is order of h squared. We know it is, the error is in the order of h squared. Now we have an idea of what does it mean. So that is the simple approach. Actually, that's built as one of the approach being taught here, Euler's method. That's looks like I gave this without any derivations here, but this can be derived either using numerical, using geometry, or using Taylor series. Probably it's in the textbook, but very simple equation: yi plus 1. So if you have a function, so if you have what is a differential equation? Probably I should have shown that the differential equation we are showing is where is that? Okay. So that's the Euler's method is for a equation similar to the one shown equation 6, that is dy by dx is fx. It could be fxy too, fxy, x and y could be. So that is the equation, and then we will solve it for different values of y, and that is a formula for that. And then we solve this for falling object velocity estimation. And so the general, that is in equation 7, I'm showing the general formula, but that's not so general than what is shown in equation 5. So I should write yi plus 1 is yi. That is very comparable to equation 5. Equation 7 is plus h f x I y I. So the equation 6 here, even we did this in lecture 1, that this equation allows us to write the general formula if we know the equation. For example, in equation 6, So then you can check this. So the true function, since it dy by dx is equal to something, you can find by x. Use it by just integrating it. So that's looks like, I'm sorry, looks like I made some mistakes here. Anyway, there are some, the error approach, there are some typos here, so I need to fix that and upload the lecture notes. I don't think this is in the one I am highlighting right now is not an equal sign. That must be another sign there. Anyway, I'll fix that. So that is the very simple form. At least let me write down the correct formula. That is, which is shown in equation 5. That is correct formula. That is yi plus 1. If you have a differential equation, dy by dx is equal to fxy. If you have a differential equation, dy by dx is equal to fxy. That is the solution using Euler's method. That equation 5 is the solution. Now, in this lecture, we are going to do higher order solution. That is, if you look at the numerical differentiation lecture, previous lecture, we saw that basic numerical differentiation we studied. And there are 3 different approaches: forward, backward, central, and we saw that forward has error order of h, backward h, and then central approach order of h squared, so it's better. Central approach is better, and then we derive higher order differentiation. If we have 3 points, we can come up with a better estimate, even for higher accuracy. I always confuse that. Higher accuracy, there are higher order. Higher order means approximating second derivative d squared fx by dx squared. Third derivative, that is higher order. Higher accuracy, even for first derivative, we can do a higher accuracy version, which we did in differentiation. Same story here. So this whole lecture is about high accuracy approaches to solve differential equation. Euler's method, and then we will go to Hume's method. We will show that what is Hume's method and what is a high accuracy, how it achieves high accuracy, midpoint methods, and then Ranjit-Gupta method. So we will see that as you go from one to another, as you go down the list, it is better and better in terms of accuracy. So these are different approaches to solve differential equation, and different approaches to solve differential equation with higher and higher accuracy. So obviously, the Euler's method that we studied in lecture 1 is a very basic approach, and we will see in this lecture that that's the only way to improve accuracy in Euler's method is to decrease the sample size, the h. If you can make this h smaller, if you can afford to make this h smaller, sometimes you don't, because you're as good as the data you have. If you don't have data, let's say we are saying if we have data at every 1 second, if we have data every 0.5 second, we can do better. But if you don't have the data, so these approaches can do even without that. So that's an advantage. So here is a summary of Hume's method. So this is the first equation I'm highlighting right now. That is the Euler's method. yi plus 1 is yi plus fxii fxiyi times x. We are always solving this equation. F x x y is dy by dx. So we will use that as a predictor equation, and then we will use, so then we will use this estimate, that predictor, 1 second, this estimate, we will use this estimate here in the function, because if you look at this, fxy, sorry, fxy, I'm writing at the top, fxy is the slope. So that is an estimate of the slope. Sometimes we write as y prime. So y prime, the first Euler's, the estimate you get from Euler's method, we use it to predict the slope, and then we find the average slope. So how do you find the average slope? The yi prime is, as I show here in the equation at the top, which I'm going to highlight now, is this. Oops, make it a little bit small. So that is the first slope that we can use it, compute it using the original equation. The second slope that we just computed using this equation, and then average. So, rather than using the original one, we are just using an average slope. And then you, once again, there's a typo. This will be yi plus fxi yi plus fxi plus 1 yi plus 1 0, which is the prediction, and divide by 2 times h. So that's the Hume's method approximation. Then there is a general form equation. If you want to program, this equation can be used. So the yi plus 1, the n plus 1 term can be written using the nth derivative. That's shown. That's the general form of the equation above. It can be shown, I did not show here, that the error is order of h cubed. So if you can compare that, I don't know if I roll it here, yes, the error here is order of h squared in equation 5. The Euler's method has error of order of h squared. So very easy that global truncation errors. And why is global? That's a good question. And I'm starting to worry that global truncation error is order of h squared. You may have, that's a good question. I cannot answer now, but check the book. All of these comes from the book. I'm going to check that and clarify that as well. Okay. It is, in the textbook, global truncation error. I was thinking that when you compute this for many points, maybe. Anyway, I will clarify that when we will revisit this when we are doing the homework. So, and I will clarify that at that point. So this picture is a very good, comparison of Euler's method versus Hume's method. So what we are doing in Euler's method here, so here we, at this point, dy by dx is fxy. So dy by dx is fxy. So if you know xi plus 1 is, as the equation suggests, is h time fxy. Very intuitive. So this is h. So this is h time fxy. I did not put the labels. Okay, so this height is h times, this is h times f xi yi. So whatever this is effect xi, yi is the height there. So this is yi. So f xi yi is that function, whatever that function may be. And the part f xi yi is the gradient there. So if that is theta, tan theta is f xi yi. So h tan theta is that height, and this height is yi, right? Yi. So that is why Euler's method is yi plus, if you look at here, it is yi plus hfi, fxi, y. You know, we can use geometry to prove that. So that's a very intuitive approach that we used even before. Now, what the Hume's method does, they're saying that this is the gradient here, which is f xi yi, and then we just predicted y for this. We did not know the y for this, and this y is not known, but we can predict it. That's a predicted equation. So you find the gradient here using so this is the new gradient at, let me say, so this is the gradient at xi. This is the gradient at xi plus 1. So gradient at the next point, gradient at the present point, average them. So that will give a moderate gradient that might look something like this. Whereas look what happened with this gradient. So this gradient just pushed the function all the way. So that's kind of an intuitive approach. So then when you use that one, and they theoretically prove that the error is indeed better. They prove that error is order of h cube. I'm not sure what this global truncation error is, but I will find that out. But it is supposed to increase the accuracy, at least as claimed by these people. So yes, so instead of using the gradient at one point, we are using average of the gradients at these 2 points, whereas for the second point, we don't know why. So instead of, since we don't know why, we use a predicted value of y using Euler's method. So use Euler's method to find the y there. So use the new y to find the new gradient there, average those two gradients. So use the new gradient again in Euler's equation to predict it again. So that's called the midpoint. So this is an example that is done here. So this example, equation 8, so that is y prime, if I write it in the regular form, dy by dx is 4 times e to the power 0.8x minus 0.5 y. You can see this in fxy format. So we always, this is the form of the differential equation we are solving with dy by dx is fxy, right? So that's the equation. So and then we also have the analytical solution. So that is the analytical solution for that equation. We studied how to solve these kind of analytical differential equation, and we are using the analytical solution so that we can compare them. So if we use okay, so let's go to, so here you can see where we computed the first, so let's go to table 1. Okay, so right, so it is an iteration, so we can go on and on using this equation to revise, and that is being done here. And you can see that from the errors, you can see, not literally, but you can see the trend here. The error is going down. You just keep on iterating. You find the new derivative and then use that, and then you find the new gradient, and then use it on the Euler's method. So find a new gradient, use it on the Euler's method, and keep on doing it, and then that decreases. I did not fill this table. Probably that's one of the, you can just program here. It is just an iteration. All you have to do is use this equation here, this equation I'm highlighting now, to write a program. Then I should also fill this, that you can fill. You can see how these values change over time. So you can keep on iterating infinitely, or until you stop at some point, and there's always chance that it might diverge. So, but the example that we use here is carefully selected that it won't diverge. But as similar to all the other approaches that we studied, like Newton method, fixed point iteration, and all of that, for some function it might not work. That's always should keep that in mind. But for this function, probably if you iterate for infinite times, the error will go lower and lower, and it will reach 0. So that's a summary of Euler's method. So that's a summary of Hume's method. So Euler's method, Hume method. Now we are going to midpoint method. So what is midpoint? Again, same intuition, better explained using this graph. So here, what we did, we've already found that the slope, computing the slope at this using the known point xi and yi is not helping. At least it introduces error. So we just said we are going to compute slope at xi and xi plus 1 and average them. Here, instead of computing the slope at xi and xi plus 1, we are going to compute the slope at xi and xi plus half, that is in the middle of xi and xi plus 1. We don't know that point. So how are we going to find the middle point? That is the first question. So we always assume, wait, xi middle point is known, because we always assume this h is known. H known. So h is known, then xi plus 1 is known, which is, at this point is indeed xi plus h by 2. So that is known. So if you know xi plus h by 2, then you can find yi plus 1. Here, equation 10 is yi plus h by 2 fxi. That's Euler's method. Direct application of Euler's method. So that is yi plus 1. And then so we just computed yi plus 1. Use that. So yi plus 1 is yi plus h f x I plus half, which is known, xi plus h by 2. That is hi plus half. So this will be xi plus h by 2, as it is shown in the figure. And then yi plus 1.5, we just computed, put in the equation and find it. So very intuitive approach and this midpoint method. Wondering, can we, it is just one iteration, because there's no way you can, there's no way to refine this, right? Whereas here, this derivative, you can always find a new one based on your supposedly new yi, and always you can refine it. So here it is just one iteration. But this can also be, I believe, this can also be iterated. How? Because the point we compute for y here, that is an estimation, right? So this can also be iterated, but even though I did not show here, if I'm going to ask a question, I'm going to ask for one iteration even for all of these. But again, probably it is in the textbook, the multiple iteration versions. If you are curious, you should check out the textbook. So, and once again, it's the same example used. So yeah, it is only one iteration is shown here using exactly the approach shown here in the midpoint equation. So that is midpoint. And then we are going to go to Ranjikuta method. What we are going to see is this is a general formula, the Ranjikuta method, that this general formula that looks like Euler's method, except for that phi there. So yi plus 1 is yi plus h times phi xi yi h. So in Euler's method, that phi xi yi h was, instead of that we use f xi yi. All right. So this phi in Euler's method, that was f xi yi in Euler's method. Now, this is a formula. We are not going to, look at how and prove or anything like this. Formula was, developed by Ranjikuta, and we are going to just trust this formula. But at least we are going to see how this reduces to all these different approaches: Euler's method, midpoint method, and Hewn methods for different values of phi. So first of all, the phi is written as a1 k1 plus a2 k2. It cannot go up to, we can, in this lecture we can study up to four different orders: a1 k1 plus a2 k2, a3 k3, and a4 k4. If we just use a1 k1, that is the first order Ranjikuta method. If you use a1 k1 plus a2 k2, second order Ranjikuta method. If you use up to a3 k3, that's third order. If you use up to fourth a4 k4, if you use all four terms, that is fourth order Ranjikuta method. And it is just application of formula, and there's really not much. But at least we can apply this. We are not getting into the theory of this, even though it is discussed in the book. But at least what I'm going to show is we will apply this. If we apply this to the same problem and see how the Ranjikuta method helps with the higher order, it helps with the error, which we can test, because at least in this example, we know the true solution. So if we know the true solution, we can see how different approximation compares with the true solution. That will be, we'll be computing epsilon t. So in this lecture, always we are computing epsilon t, because the true error is known. It's a good way to test different algorithm and compare. So now what is k1, k2, and k3, k4? K1, k2, k3, and k4 given here. The k1 is just the function itself, that is dy by dx. K1 is f xi yi, that's the function itself. That means we define the function as f xi yi is dy by dx, right? Now k2 is f xi plus p1h plus yi plus q11h k1. and then K3, and bear with me, let me read this through, xi plus p2h, and then yi plus, different values, q1, q21h, k1 plus q22h, k2. What you can observe here is uh, K3 has K3 has K2 and K1 in the equation. K2 has K1 in the equation, and obviously K4 has K1, K2, and K3. So the previous coefficients are used in the present coefficient. So obviously K1 uh, doesn't have anything. So if it is a, let's write the first order Ranjikuta method. The first order Ranjikuta method equation. Sometimes we call it RK, RK method, just for simplicity. First order, wait a second, first order RK method will be what? yi plus 1 is yi. Now for first order, phi is just a1, k1. So plus a1, k1 is f xi yi plus h. And for first order Runge-Kutta method, we assume a1 is 1. So we assume a1 is 1, then it is yi plus h f xi yi, where a1 is 1. So it just reduces to Euler's method. So the first order is Euler's method. Second order is going to be, you can show that when you write the formula, the second order is going to reduce to midpoint method. If you select these values for AI, it is going to reduce to Hume's method. The midpoint method, if you select those values, it will reduce to Hume's method if you select the next set of values. So second order is equivalent to two other approaches we studied previously. One is midpoint, other one is Hume method, based on what we select for A1, A2, and P1, Q1, those coefficients. So that also means that we can select other values for A1, A2, P1, and Q1, which we are not discussing here. And then, so that's second order. For third order, the values were already selected here. This is for third order. We did some selection of values based on some reason. So in the end of the day, the third order Ranjikuta equation comes to a very simple formula. yi plus 1 is yi plus h by 6, k1 plus k2 plus 4k2 plus k3, where k1, k2, and k3 are given in equation 15, 16, and 17. Same for the fourth order Ranjikuta method, where you will have all four K1, K2, K3, and K4. But as you can see, there are many different scenarios, but it was all given. So end of the day, it comes down to this set of 5 equations. Third order comes down to this set of 5 equations. That's all we need to know. But with that, what we can do is we can implement these methods using a program and see how they, how they compare. And that is exactly what is done here in this equation. So they compare Euler's method, Hume's method, RK, third order and fourth order Range-Kutta method. They are showing it as in terms of effort. That means how many iterations you have to do versus percentage relative error. As the effort increases, the Euler's method settles down at a certain error, whereas you can see Hume's third and fourth, the error which is displayed, the error is an order of h squared something. The error is not shown as in the order of h squared, but it is shown as absolute value error. But what is sure is that as you increase the order, error is going to reduce. It would be nice. I'm not going to assign this as a project, but it would be nice to implement this using this example. So take this example, implement Euler's method, midpoint method, Hune method, and Ranjakuta third, fourth orders, and then you will keep on iterating it more and more, and you can see how the error is reducing as you do more iteration, and you will obviously see that the Ranjakuta fourth method is going to do much better. You can always you will always compute the absolute error because the true value, true solution is no. So that's it for differential equations, a numerical method to solving differential equations. So I know there's a question here about this. I will clear that up. At least I will fix it in the lecture notes and find out what is your global truncation error and put it there. I will update the lecture notes. And probably I assigned one of these questions as homework, but there are more questions also. What you can do is what you can do is you can write a program to implement all these. You can write a program to generate a graph, something like this, for this problem. The problem that was discussed either in this problem shown in equation 12, or one of the problems given in the in this equation in these homework questions. So that implementing that and in the same that will give you a good satisfaction of learning these different methods for the differential equation. So I will take up partial differential equation in the next class. So what I'm going to do is use, as I promised, I'm going to use the remaining time to review and do some homework. Plan is to do all the homeworks. Let's see how that goes. So give me 1 second to find that stuff. Lecture 1. Homework 1. All right. Okay. So I thought I would quickly go to lecture 1 to see what we just studied. This is how this was a lecture 1, and then we just talked about a falling object, and then we said we can approximate uh, the velocity of the object as like that, and then we wrote an equation that Vti plus 1 is Vti plus that is h. Sorry. So this is very similar to what we just studied. So this is h, and that's the function. So this is dv. So vt is dx by dt, right? dx by dt. So dx by dt. So this is like y. So y instead of y, we are using b. b ti plus 1 is b ti plus ti plus 1 minus ti times that function. So so that's Euler's method that was introduced as Euler's method. And then we use that to compute the velocity at different points. That's an example of, we did that without going through all this math. But now I think we are a little bit better off. So I thought I will just point that out in lecture 1. Now, lecture 2, sorry, let me open homework. Homework 1. So homework 1 is question 1 from lecture 2. So lecture 2, question 1. Question 1, Euler's method for velocity update. So consider balloon dropping problem that we discussed in lecture 1. Assume that balloon was starting 0 velocity, and we had to write an algorithm. So that probably, for those without a programming background, that you probably had some, confusion about, for example, how this progresses with time, from the algorithm progress like this. Let's say this is the initial, and then from here to here, you will do one step update, and then from here to here, you will do the next update. Here to here, you need a third update, and like that, every step you will update. So that is the algorithm. Let's look at the answer and see if I can. So this is the algorithm. So if you think about this algorithm, it needs some input. Okay, I did not show it here, but it would be nice to show input. So what is the input to the algorithm? So input to the algorithm will be vk minus 1. So the previous velocity. So algorithm goes from here to here. It goes from here to here, here to here, here to here, here to here. So that's the algorithm, one step. So the output, I will write the input output form like this. Vk is, I will call it Euler's. But this is a pattern I used later in the lecture notes, so I thought I would follow. So Euler's, EULER, and then Vk minus 1. So this is the input to the algorithm, and this is the output. So it is like a system. Input, you give the input vk minus 1, the algorithm will the next estimate vk. Now this algorithm needs, so this is the name of the algorithm. So that's EULER. So that's the name of the algorithm. If you are programming in C++, maybe you will create a function that will take input as vk minus 1 and then output as vk. I always, in this, at least in the lecture, I write it as algorithm because you can program this. I don't want to just do everything in C++ because you want to, you will have to learn many more languages. So if there is an algorithm, you can always code it. So that the remaining part is called coding. So you can code it in any language you want. But important thing is to straighten out the algorithm. Once the algorithm is straightened out, it is easy to see the logical problems. And once you fix all of that, you can go and code it in any language you want. So that's the algorithm name, and an input and an output. This algorithm needs 3 constants. So you can send it this constant, or you can just define it there. If you are programming, you can define this as constant, global constants. For example, these are all could be a global variables. That's a mass. So the constants are m, c, and G is the gravity acceleration, N is the mass, and C is the drag coefficient. When the thing drops, there's a coefficient that the force that acting on the opposite side of the velocity. So if you these constants are assumed, no. In the right program, you had to declare them as constants, and then you had to initialize them. So that's an algorithm to compute these. Okay, question 2 from lecture 2. The following pseudocode can sort the array A of length n from smallest to largest element where the possible values for A. So that's this. You can. I probably introduced when I introduced this. I said that this is not much relevant to what all the theoretical stuff we are going to do, but it again gives a introduction. I use this to help you write some for loops and while loop in C++. Other than that, it is probably not much related to what we studied later. So what is happening here is, you start with the first element, and then you just go in this direction every time. So if you want to switch, if you want to order them in increasing order, you will just start with this, and you will just look at 8 and 4. You will see 4 is smaller than 8, so you will put them back, 4 and 8, 5, 6, and then you will go to the next step. You will look at 8 and 5. You will compare them. So 8 and 5, 5 is smaller than 8. So what you do, you will just 5, 8, 6. And then we will go to the next step. You will see 6 and 8. So 6 is smaller than 8. So you will switch them. 6, 8, and then you will come back, and then you will start from here and do it. You will just finish it until everything is in order. So that is described in this algorithm. So n is the number of elements. So in this example here, n is equal to 4. N is equal to 4. So that means we stop at 4. So we don't need the remaining. You would stop at 4, and then k is equal to aj. So j is equal to 2. So the second element, you will put the second element in your array. So aj is 4 here when you are doing it for the first time. And then I is equal to, you will go from 1 to I is equal to 1. And then if I is greater than 0, and then you just combine them and do that switch. This, if you just compare this algorithm to all the algorithms that we implemented later, bisection method, all these root finding methods, Newton-Raphson method, probably they were not this complex, and compared to different kind of sorting algorithm you did. Probably all of them were to understand them and to implement them were much easier. But this is classical sorting that we always do when you do some programming. We will, in the first or second class of programming, you will do a sorting. So that's the good exercise to understanding what an algorithm is, and then what happens at every step of the algorithm. So I hope that helped there. And the best way to get the answer is to program this and display this. So the best way to get this answer is not by hand. To code that, and then every time you come to a point, you just display the answer. That would be, you will never make a mistake. But if you do by hand, you can do it, but probably there'll be some, you might end up doing some mistakes. So that's third question. Again, we were going to study all the theory of this. We know that the question is, what is the output for when you call this function like this? That is x is equal to 0.2, x is equal to 0.2, epsilon is equal to 0.05, and max iteration is 4. So if you give those input, that this is a very classical algorithm, that is the algorithm name EXPX. I just named it to indicate e to the power x, and then input is x, epsilon s, and max iter, and then output is whatever the output is. This is the output. So that is output. We did not study e to the power x Taylor series anything at this point, but I still gave this as an again to introduce what an algorithm is. So, but we later studied that using Taylor series, we can write e to the power x as 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. So that we know, but in this question it was not given. So, but if you look at the algorithm, that is what the algorithm is doing. So if you figure that out, it would be much easier. We can even do this by hand. We don't need to code this algorithm. We can do this by hand. So first, let's see if that is indeed the case. So I'm saying while repeat is equal to true, we are doing solve equation equal to 1. And then solve all. Solve stands for solution. All is solution. The solution is initiated as 1. And then we are increasing n for I is equal to 1 to n. So is sol plus xi over I factorial. Right. I factorial. So that is this term xi over I factorial. So that is the function being implemented there. So we are basically implementing 1 plus x squared over 2 factorial, x cubed over 3 factorial. And so we were going to, this algorithm is going to increase the number of terms. So it is going to say e to the power x is equal to 1, e to the power x is equal to 1 plus x, and it's going to say e to the power x is equal to 1 plus x x squared over 2 factorial, e to the power x is equal to 1 plus x cubed x2 over 2 factorial, x cubed over 3 factorial. You're going to increase the approximation. You're going to make the approximation better and better. And every time we are going to compute this relative error, which is 100 times previous approximation, current approximation minus previous approximation divided by current approximation. What I did not, probably this is, I should have put it here, an absolute value here. Without absolute value, sometimes this might go negative. I don't know if you encountered that problem. Probably if you did not, probably that's only because you was lucky. The right algorithm should have that absolute, which we implemented later in the lecture notes, but this is something I need to fix. So compute the epsilon error, and then you check if the epsilon A is, we did this many times. All the you did this many times in your root finding code. You check whether your relative error is smaller than the threshold or the iteration will reach max iter. So for max iter, we have 4. So if you reach 4 iterations, so we were never going to go beyond this. And then if the max iter is, if one of these reach, we will exit. So what is that answer? So probably if you implement this in coding, that's going to be faster. But if you have to do it by hand every time, you compute the first approximation for first approximation, there's no epsilon a. Once you have the second approximation, compute epsilon a. Compute epsilon a every time you increase the order, and you stop when every time. So there will be an epsilon a here. There you can compute an epsilon a here. You can compute an epsilon a here. At this point, you had to exit anyway. But if the epsilon a was less than epsilon s before, you would exit. So that's it. That's the yeah. That's how you will find the answer by hand. But the purpose of giving this question was to familiarize with the algorithm. All right, so we have time to go to homework 3. So let me find homework 3 and be back. Let's see. Homework 3. Sorry, homework 2. Homework 2 is what I need to find now. But I uploaded the answers to all the homeworks, except for the ones that were not, the due date is over. Lecture 3. Okay, so why don't I do a quick review of lecture? This is lecture 3, error analysis. So whatever I introduced in lecture 3, it was used even in today's lecture. In today's lecture, we just saw this. We just computed this in today's lecture, lectures 18. That is, true percent relative error is true error over true value times 100%. So the true error as a percentage of true value is the true relative percentage error. True error is not very useful in real application, because if you know the true value, why would you compute it in practical application? So we'll only compute true error to understand. For example, today, different type of differential solving ordinary differential equation, Runge-Kutta methods, big point method, Hewins method, Euler's method. We want to see how they are all doing, how they are comparing. So we can implement them, write a program to implement them, look at the errors as a comparison of effort, and compare them. So true error is useful for that. But the relative error was useful in actually, let's say I need to find a root for a function. I don't know the true root. Then we will just do the first iteration, find a root, second iteration, find another root, and then find the relative error. So that is probably I should even here I should put this absolute value. That's kind of missing. It should be. I will correct this in my lecture notes. That if it is not, it is always the error. This percentage error that we compute is always a positive value. We don't the epsilon s, which I'm going to talk about, the specified error tolerance. Again, that's a positive value. So the absolute sign should be there. So approximate error. Approximate percent relative error is approximate error over approximation in percentage. So the important thing is specified error tolerance. Let's say we are doing some iterations. And we want to make sure the error is the number we get is accurate of this n significant numbers, and is shown here. If you want the number to be n significant number, then This is the, you had to iterate up to this point. That's something. Rather than, okay, I will iterate 50 iteration. So if you do 50 iteration, let's say you are finding and you are setting your program to 50 iteration, you don't know what is the accuracy you're getting. But this gives, why do you have to do 50 iterations if you can get the required accuracy in 7 iterations? So that is it. This understanding, this helps us, avoiding unnecessary work. The computer doesn't need to work that hard. You can just tell. So if the required accuracy is n significant digit, you have to iterate only up to epsilon a until epsilon a less than epsilon s. Epsilon t, there's no point. Epsilon t won't be used in real applications anyway. If you know the real solution, what is the point of computing it using approximate methods? So that's it for this lecture. Then I was just showing how to do this e to the power x, the same algorithm we already saw. Okay, this lecture is all about errors. So then we talked about different types of errors, right? So truncation errors and round off errors. So there are 2 types of errors, well, 3, depending on how defined. It's approximation, truncation, and round off. So approximation, truncation, and round off error. So did I give an example for approximation error? Well, it looks like I had an approximate error. Yeah, when for approximation error, I give this computing velocity. That's we approximate it. We have many approximations there. For example, we use Euler's method to approximate the velocity. dv by dt is x I plus 1 minus xi over ti plus 1 ti. So that's an approximation there. So whenever we do some kind of approximation, we call it approximation error. Truncation is e to the power x is given by this equation. Now, truncation is what if we stop in just one approximation. E to the power x is 1, regardless of what x is. So that's an approximation. But if e to the power x is 1 plus x, if you use 2 terms, it is 1 plus x squared by 2. If you use 3 terms and so on. So you will have to truncate at some point. So that the remaining is called the truncation error. The other one is round off error. Very important type of error. And this error helps to understand about computer implementation and so on. So this error, we saw how this error comes. When you try to implement floating point number, this type of error comes. And then we saw that we gave an example of how floating point implementation is done. The question 1, we have the floating point implementation. We write them in this form, and then the number is 8 is equal to n times b to the power e. B's base is exponential and m is Mansa, and then I gave different ways to have this Mansa. For example, if you have 3 plus 3 plus 6, 7-bit number, and then you allocate some bits for Mansa, some bit for exponent, 1 bit for sign. 1 bit is enough for sign, either it is negative or positive. 1 for sign of exponent, 1 for sign of the number. And then there is a rule that that's probably this probably it was a little bit confusing and for many of you, that when you approximate in decimal number, for example, let's say 0.00843, we write this. When you bring this to floating point representation, we don't write it 0.0084. Let's say we have enough bits, still we don't write it 0.843 times 10 to the power 0. We bring it 0.843 times 10 to the power minus 2. For example, then bringing that gives us what was after these two. If there were 2 digits, then that allows to write that digits, what are those digits here, and then 10 to the power minus 2. So that is a rule that when you do this floating point interpretation, there must be a number next to the 0. So that rule must be followed. It is followed in the IEEE standard. So this is a very simplified version of IEEE standard. So IEEE standard follows that rule. And then each of these is 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3, like that. For Mandisa, you will multiply first one by 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, like that. And then, given a number, you can just put all the values according to the definition, and you can find the number. So the question on figure 5 shows a hypothetical floating point number set for a machine that stores information using 6-bit words, very similar to the one in the lecture notes. The question is to write all the possible numbers. So you're already given, the minimum number is, there are two ways. If it is positive, that will be 0.0625, negative 0.093. So, and also the structure of the number is, the first two are the Mandisa. First two are the Mandisa, and then exponent. So you write all the values for Mandisa, and then you write all the values for exponent. The important thing is, what are the possible values for Mandisa? So Mandisa are 2-bit. So many of you might think 0, 1, 1, 0, 0, 0, 1, 1. So these are the 4 possible values for Mandisa. But we don't take that. We don't take these two. This we don't take. Why? For the same reason I just talked about here. If when we have a situation like that, we don't write 00843. We'll always, there should be a number next to the decimal point. If that is the case, because this is a number next to the decimal point, you can only have 2. So 1, 0. If you just look at this, the Mandisa is always going to be those either 1, 1 or 1, 0. Either 1, 1. You can just, we will only have to do is fill the table. That leaves us 2 exponents. So how many possible values we can have for the exponent? And then you can just write all the possible values for that. That the exponent can have 7 values except for the 0. So sine of e, magnitude of e, sine of exponent, yes. So it can also right, 0, 0, 0, 1, 1, 0, and 1, 1. So what? Right. So exponent can be. So if there is a 2-bit number, exponents will be, say, 2 to the power 2. So 2 to the power 2 is positive numbers. 2 to the power 0, 0, 0, 1, 1, 0, 1, 1. Then for the negative also you can write 0, 0, 0, 1, 1, 0, 1, 1. But this is negative. But what is the difference between positive 0 and negative 0? No, there is no difference. So that's why we don't repeat that. So how many exponents you can have? 2 to the power n minus 1. If it is 2, if it is 3, then that will be 2 to the 3 minus 1. Here it is 2, so that will be 2 to the 2 minus 1. So 2 to the 2 minus, so this will be This will be 2 to the power 2, and that will be 2 to the power 2 minus 1. So that will be 2 to the power 2 times 2 to the power n minus 1. So that will be 2 to the power n plus 1 minus 1. Anyway, if you have 2 bits, you will have 7 numbers. So that will be 2 to the power n plus 1 minus 1. That will be 2 to the power 3 minus 1, 8 minus 1. So that I explained why for exponents we will have one number less from all the possible numbers, because 0 cannot be negative and positive. Mandisa explained why the first digit. Again, this is a pretend number based on IEEE standard, but you should know why the IEEE standard was developed like that. Probably I don't have time to finish this up, but definitely we will start from the next class, and we will have more time for homework from the following class because there's no more lecture remaining. The plan is to finish all the homeworks and kind of have a review discussion about what we all study. So we will continue. The Mandisa can start with 0. No, it can start with 0. Yes, I think I didn't see that question. Yes. So that is exactly why, if you look at all the Mandisa that we use here, always starts at 1. That is a convention. IEEE, I mean, real computers, probably they don't use binary. They probably use hexadecimal. So they will have a slightly different system. For example, for decimal numbers, the possible numbers. So if you are just doing, let's say computer is decimal, then 0. This first position cannot be 0. It can be anything between 1, 2, 9. So this, probably I did not write that in the lecture note, but it is in the textbook that this number, that first digit of Mandisa, I'll call it M1, should be less than B greater than 1 over B. If it is base 10, that base 1 over 10, the first digit of Mandisa 10. So all of these satisfy that. 1 to 9 satisfy that. Let's say it's a hexadecimal number, then it will be 1, 2, up to 15. Some computers use hexadecimal numbers. Then it will be like that. If it is binary, that is 1 over 2, M1, 2. In binary, there are only 2 possibilities, 0 and 1. Then this M1 can only be 1. So that's why, all the first digit of Mandisa needs to be 1. All right, everyone. So we will continue. So one more lecture to go. All the remaining time, we will do reviews. I hope the project is going well. As I said, please do the project entirely on Reflect, because when you copy and paste, we don't know where you copied and paste, and that's not good for anyone. So we will enforce it this time pretty severely that we want to see your history of project.